Hello! In today's lesson, we are going to look at damped simple harmonic motion. We will perform a dynamic study that will lead us to a differential equation. I will explain the different types of damping, and we will see an application of this underdamped simple harmonic motion. Recall that in the ideal case we studied in previous lessons a spring oscillating in the absence of friction. The only forces involved were the weight force and the spring restoring force minus kx. The motion. Describing the spring in this case is an ideal simple harmonic motion. We see that its amplitude is constant, and the elongation is described by this equation, a sine of omega t plus phi with the omega, with the pulsation equal to the square root of k, the elastic constant of the spring, divided by m. If we take friction into account, we must include a force opposite to the direction of motion, minus Cv, which we see here, where C is the coefficient of viscous friction. If we now pose summation of forces equal to mass times acceleration, we would get minus kx minus Cv. And rearranging, we are left with this differential equation. What I have done now is to divide all the terms by m. Then this k, the elastic constant of the spring, I have replaced it by the value that we all know, mass times pulsation squared. And we are left with this expression. Next, you see that I have changed the omega by omega sub 0. This is to differentiate it from the omega that we will see in a moment, proper of the oscillations with damping. Is this the omega we have seen in a moment? This omega is the one we have seen so far. It is square root of k divided by m, and it is the pulsation of the undamped oscillations. So, the differential equation is this. In the bibliography, you can find it written in this form, where lambda is the damping factor, which is nothing more than c divided by 2m. Summarizing, this is the differential equation that defines the damped simple harmonic motion, where we see that it has acceleration, velocity, and elongation terms, where lambda is the damping factor, which is equal to c divided by 2m. C is the coefficient of viscous friction, and omega 0 is the omega that we have seen in all these previous lessons, and which is equal to the square root of k divided by m. It is the pulsation of the undamped oscillations. And what is the solution of this differential equation? Well, the solution depends on the value of lambda. It depends on whether lambda is greater than omega sub 0. In that case, we would have an overdamped motion. We see it represented in the graph in green, and we see that the mass does not oscillate. It does not exceed the equilibrium position. If lambda is equal to omega 0, the motion is critically damped, and it is the case in which the mass arrives sooner to the equilibrium situation. And if lambda is less than omega 0, we are dealing with an underdamped motion. We see that in this case, shown in blue, the mass does oscillate around the equilibrium position. But we see that the amplitude is not constant, as in the ideal case when there was no friction. Well, in the latter case, the elongation is given by this equation. A times c minus lambda t times cosine of omega sub 1 t plus phi. We could have represented it by a sin. You know that the only difference is the initial phase. In this case, we see that the pulsation is omega 1, not omega 0, which is what we had when the oscillations were undamped. The relationship between omega 1 and omega 0 is shown here. You can see that they only differ in one term where lambda is present, which is the damping factor. Omega 0 is the one we already knew, square root of k divided by m. It is the pulsation of the undamped oscillations. And then lambda is the damping factor, which is c divided by 2m, where c is the coefficient of viscous friction. Here I have represented that elongation in blue, and I have put in red the envelope, that decreasing exponential that multiplies the cosine. then we no longer have a constant amplitude A as it was in the ideal case without friction, but we have a decreasing exponential which causes the oscillations to become smaller and smaller until finally the motion ceases. If lambda, the damping factor, is very large, the oscillation will fall rapidly and the motion will last very short. If lambda is smaller, the oscillation will damp more slowly and take longer to reach zero. Then, the motion described by a mass suspended from a spring in the presence of friction is like this. You see that the amplitude is no longer constant but decreasing. And finally, an example of damped simple harmonic motion. The swing. I'm sure that when you were little you swung many times. Jota and Amanda still do. The other day, Amanda was sitting on a swing. Jota pulled the swing away from the balance position and let go, and the swing started to swing. Jota started to wasp thinking it was an ideal simple harmonic motion, but Amanda's screams, asking him to push him, made him realize that it was a damped simple harmonic motion, and that if we don't apply an external force to dampen the friction, the oscillation has less and less amplitude, and at the end it stops, the swing stops. Here is a summary of the differential equation of the damped simple harmonic motion. The three types of damping, the underdamped, overdamped, and critically damped. And the solution of the differential equation for the underdamped simple harmonic motion. See you in the next lesson.